But, in Organic 2, most of our discussion for functional groups revolves around their reactions. And when it comes to alcohols, there's a lot we can do with an alcohol. Typically, in a single reaction, you can convert an alcohol to an alkyl halide, to an ether, you can eliminate it to form an alkene, and you can oxidize it into various carbonyls, depending on both the alcohol that you use as well as the reagents you use. That could be an aldehyde, it could be a ketone, and in certain cases it can even be a carboxylic acid. So a lot of different things that we can do with it. But before we talk about what you can do with an alcohol, we always want to talk about how do we make them. So it turns out we've already learned a number of different ways to make alcohols. At this point, we should comfortably know 5 different ways to make alcohols. Most of these are things we learned in Organic 1, such as alkene hydration, oxymercuration, and hydroboration. These are all ways to make alcohols. Of course, the first 2 give us the Markovnikov, or more substitute alcohol, whereas hydroboration is anti-Markovnikov and gives us the less substitute alcohol. We also learned about dihydroxylation, osmium tetroxide, and NMO, which gives us a diol, or 2 alcohols. And we've learned some ways that we could use SN2 to make an alcohol. But we're going to add new ways. And by far the most important new way that we're going to add is reduction of a carbonyl. So we've seen before that carbonyls are excellent electrophiles. In fact, there's so many different reactions of carbonyls that we can talk about and will talk about that we'll be spending a long time in this course talking about reactions of carbonyls. So what kind of reagents do we need to do a reduction of a carbonyl? Well, it's the addition of H- or hydride. And so there's 2 very, very common reagents that we use for this reaction. NaBH4, sodium borohydride, and LiAlH4, which is lithium aluminum hydride, which we commonly abbreviate as LAH. Now, while there's some difference in the strength of these reactions, they behave in very similar ways. So the metal on them is just a counterion in both cases. But what we have is a group 13 element, boron or aluminum, and that's bonded to 4 hydrogens. And what we'd want to consider is, what are the electronegativities of these elements? So hydrogen is 2.1, boron is 2.0, and aluminum, which we find below boron, is 1.5. So what we have here is something, fairly unusual. And that's that we have hydrogen being bonded to elements that are actually less electronegative than hydrogen. So these boron-hydrogen bonds, as well as these aluminum-hydrogen bonds, are all polarized toward the hydrogen. And so these reagents, to an extent, behave like H-. Now, they're not actually H-. You can buy, reagents with H-, such as sodium hydride, NaH, and that's even more reactive. But that's something we normally don't use in this context. So why do we have different reagents? Well, it depends on what we want to react. So NaBH4 is great for aldehydes and ketones. On the other hand, LAH, which is much more reactive, the reason it's more reactive is because it has a larger electronegativity difference between the hydrogen and what the hydrogen is attached to. So LAH, in addition to aldehydes and ketones, can also reduce esters, amides, and carboxylic acids. But right now, today, we're just going to look at the reduction of aldehydes and ketones. We'll talk about the LAH reduction for esters, amides, and carboxylic acids at a later time. But the basic reaction is we take an aldehyde or ketone, doesn't matter which one, and we add sodium borohydride to it, and then one of those hydrogens attacks the carbon of the carbonyl, and we push the electrons up onto the oxygen. Giving us an intermediate that looks largely like an alcohol, just missing its proton. LAH functions in largely the same way. The H- attacks from the lithium aluminum hydride, and we get a pretty much identical looking intermediate. From here, at least for the sodium borohydride reaction, typically these use some sort of alcohol as a solvent, so that O- removes the hydrogen from the solvent, and we get an alcohol as the product. Now, this is what we show as the mechanism in this course. In reality, this mechanism ends up being a lot more complicated because it's thought that the sodium borohydride is capable of reacting with, say, methanol as the solvent. To form all sorts of intermediates where one or more of the H's on sodium borohydride have been replaced by the alcohol groups. And it's believed that some of these types of species are actually more reactive than the sodium borohydride itself. So it's one of those mechanisms that looks really straightforward. Turns out it's actually quite a bit more complex than what we see here. With LAH, the reaction is largely the same again, and we'll revisit its reaction with aldehyde, with esters and carboxylic acids and amides in a later chapter. But reduction of aldehydes and ketones is a really important reaction in many contexts. So if you ever see this compound, this is a compound which you'll see biologically. NADH. If you ever see NADH, NADH helps with electron transfers. So you see that, you know, an oxidation or reduction is going to be taking place. And if NADH comes into contact with pyruvate, it will do a reduction on pyruvate, especially if there's no oxygen around. If there's no oxygen around, what happens to pyruvate? Well, it gets converted into lactic acid. And you can see that it's that exact reaction that we just talked about.